Good afternoon. My name is Lucas Silva, and I'll make a presentation about the fatigue behavior of bolted joints for rack structure. I'm a master student at Faculty of Engineering of University of Porto. The presentation will be divided into 6 topics. They are Introduction, Experimental Details, Test Summary, Delta Sigma N curves, Failure Modes, and Conclusions. This investigation work is based on fatigue of double shear bolted joints, which are a typical connection in racking system. These joints are submitted to fatigue because there are many storage and retrieve machines that carry weight goods at high speed over them. According to the current industrial practice, bolted joints are tightened by hand, in other words, with no torque control, leading to the concept of snug tight bolts, which behave similarly to non-preloaded bolted joints. Nowadays, Eurocode 3 has no reference about fatigue design for snug tight joints and thin-walled, cold-formed steel profiles. Therefore, Fast Code project aims at providing fatigue design rules for Eurocode 3. Experimental details. This image shows the specimens used in the experimental fatigue tests with its dimensions in millimeters. 3 different types of specimens were used. At the left, we can see single bolt specimens. At the center, multiple bolt specimens, and at the right, single bolt specimens with reduced net section. The plates are all 2 mm thick. The specimens were made of S350 GD steel with zinc coating, and the tests were carried out at Laboratory of Technological Testing from the Department of Mechanical Engineering at the Faculty of Engineering of University do Porto, with 2 MTS servo-hydraulic machines with maximum load of 100 kN and 120 kN. In this slide, it's possible to have an overview of the performed test matrix. Preliminary tests were conducted with M16 bolts, while reference condition tests were performed with M12 bolts. 2 types of bolt arrangements were analyzed, single and multiple. 2 types of hole production, punched and drill. 3 different stress are ratio 0.1, 0.3, 0.5, and 2 preload levels, preloaded and snug tight. The preloaded level is 70% of bolt ultimate force, while the snug tight is 25% of 70% of bolt ultimate force. In order to analyze the different stress R ratio, a mean stress correction for the bolted joints were proposed. Tata, in its work, Development and Application of a Fatigue Class Catalog for Riveted Bridge Components, proposed the following equations for mean stress correction. The chosen equation was the one proposed for mild steel post 1900 with R bigger or equal to 0. After the mean stress correction, the obtained results were treated under ASTM E739 procedure. The results were compared with Eurocode 3 proposed curves. In this slide, it's possible to analyze the results for a single bolted joint with preloaded bolts and stress R ratio 0.1 according to ASTM E739. The graph contains the mean SN curve, the mean plus minus 3 standard deviation, and the Eurocode 3 class 112 curve. The Eurocode 3 class 112 is suggested for double covered symmetrical joints with preloaded high strength bolts. The mean minus 3 standard deviation obtained curve has a slope of 5.3 and a fatigue strength of 108 MPa. it is possible to verify that the slope of the obtained curve is quite different from the slope proposed by Eurocode 3. In this slide, it's possible to analyze the results for single-bolted joint with snug-tight bolts and stress R ratios of 0.1, 0.3, and 0.5 according to ASTM E739. The graph contains the mean SN curve, the mean plus minus 3 standard deviation, and the Eurocode 3 class 9 curve. The Eurocode 3 class 9 is suggested for double covered symmetrical joints with non-preloaded injection bolts. This class was chosen for the comparison because non-preloaded injection bolts could behave similarly to snug-tight bolts. Once again, it's possible to verify that the obtained curve has a different slope than the Eurocode suggested curve. The mean minus 3 standard deviation obtained curve has a slope of 8.5 and a fatigue strength of 114 MPa at 2 million cycles. Here it's possible to analyze the reduced net section data. They seem to have a higher fatigue resistance than the reference condition plate. This is a result that our team is still trying to understand, but certainly attributed to some initial plastic yielding that impact on stress distributions or any possible initial crack shielding. In this slide, we can analyze the results for multiple bolt connections. They seem to have a lower fatigue resistance than the single bolt connection. This result can be explained by the fact that was considered 50% of the load on each bolt line, and probably the distribution of load on bolts on snug-tight condition is different from that, with possible slight higher load transfer on first row of rivets, motivating the failure always in that row. In this slide, it's possible to analyze the results of two preliminary tests with M16 bolts and single bolt connection. The results for M16 bolts fit perfectly in the range obtained with the help of ASTM E739 procedure. Here it's possible to analyze the results for multiple bolted connection with drilled holes. They have a lower fatigue resistance than the punched bolt connections. This result can be explained by the poor quality of the drilled holes, as can be seen on top, which, due to the thin plates and inappropriate drill tip angle, resulted in a non-perfect circularity of the holes. In this slide, we will be discussing the failure modes. As the image shows, the crack position moves away from the center of the hole as the stress range decreases. The specimen 1, the one with higher stress, has the crack in the center of the hole, while the specimen 5, the one with the lower load, has the crack outside of the hole border. This can be explained by the fact that in higher loads, the contact pressure by the load is not high enough to prevent slipping, and the stress concentration around the hole cannot be neglected. With this study, it's possible to get to some conclusions. The experimental data obtained submitted to ASTM E739 procedure showed that the Eurocode class 90 curve for fatigue design seems to be conservative for high cycle fatigue and unsafe for low cycle fatigue. This work evaluated a slope M equals to 8.5 and a delta sigma of 114 MPa for snug tight bolt joints under fatigue loading. Eurocode class 112 also seems to be conservative for high cycle fatigue projects. ASTM E739 procedures evaluated a slope M equals to 5.3 and delta sigma of 108 MPa for preloaded bolts. Multiple bolts connection with drilled hole showed lower fatigue resistance than all the tested specimens. This result can be explained due to the poor quality of the drilling, as we saw in the previous image. Currently, the investigation team is working on crack growth simulations with the help of software Frank 3D. The main objective of these simulations is to evaluate the critical size of the crack and the number of cycles to failure. The results obtained with these simulations will be presented on future articles. Here we can see the reference used in this study. The authors would like to show their gratitude to Fast Code Project, Research Fund for Coal and Steel, Instituto da Construção, Universidade do Porto, SciTech, and Fundação para Ciência e Tecnologia for the conditions provided to the present research.